good morning, everyone. Thanks for showing up, and you're doing a great thing for you. It's a nice seminar series that you will learn a lot of details about C++. And today, so I'm Gökberk Kabacoğlu. I'm one of the members of Scientific Computing Group at Durham University. Today we're going to talk about data structures. So let me start sharing the slides. Please feel free to interrupt at any point by a message, or you can speak up as well. So today's topic is going to be data structures. Data structures, it's an essential topic actually, because it's a sort of a way of organizing and storing data so that you can access and modify this data efficiently. It is pretty crucial, especially when there's a huge increase in data that we play with in programming. And the choice of data structure is pretty important for the speed, the efficient use of the computational resources, and also the memory usage of the resources that you have. So you have to first understand the code or the program that you're writing, and also the resources that you have, so that you can optimize your code for that particular application based on the resources you have. Okay, so it's like, you can think of it like your room, and then your clothes in your room. You can put them everywhere. You can be as messy as you want to be. You can have your own organization within that messiness. But if you want someone else to use the code or use your room, your clothes as well, you better organize them in closets, right? And then you can write some notes somewhere just to say that, okay, this T-shirt is on this rack, and so on and so forth. So it takes faster to reach out those T-shirts or pens in your room if you have some sort of organization. That's why data structures is an important topic, is an important thing to consider when you code in C++. So what we will cover is that we're going to have a short introduction to data structures, and possibly you already heard about abstraction. So we're going to discuss a little bit the abstract data types, abstraction, encapsulation, and then you will see there are two main data structures, linear and nonlinear data structures. So we're gonna discuss the linear data structures. Among them, you will see structures, arrays of structures, AOS, versus structure of arrays, SOA. So you will learn how to use, or which one to use depending on the application. And briefly, we'll discuss stacks and queues, which barely show up in scientific computing, but we'll discuss. Finally, we're going to look at some nonlinear data structures, and a particular example we would like to focus is binary trees. Okay? So let's get started. The data types that you can see in C++. So first, mainly I'll talk about C, and then I'll give some details about C++ too. So you have some primary. First, let me also get the laser pointer here. So we have some primary data types. They are built in the program, like integer, int, character, floating point, and void. So void is just, maybe you already know, but in case you don't know much, void it's not like a meaningful data type. It is used usually to just say that there's not going to be any output, or there's not going to be any input to the program. It's like a data type that you don't actually use. Okay, but you have to define. That's language. Language needs to learn what will come out or what will enter the program. You have some derived data types from these primary data types. So these can be functions, arrays, like arrays of integers, pointers, and then some references. These are all constructed from primary data types. And then you have some user-defined data types, like a structure, union. So structure is basically, it stores the primary data types, right, in different memory locations. Union is, you can think of this as a data type, but it puts everything into one memory space, some place in memory, some location in memory. So it's a different form, and but again, there are some applications where you will actually use them. And then there's enum and type def. These are basically you use for defining some data types, just user-defined data types. So what is not available in C is Boolean is not available in C, so you include it through this include studiobool.h. But in C++, it's already embedded there, so you can define a true or false in C++. But in C, you have to define it in the header to be able to use it. And string, it's just a character arrays in C, so you define it as again using the character primary data type. Okay, so the data structures basically they combine these in systematic ways, and you'll learn how to do those. Okay, so you can combine them in a linear structure. So these are sequential. It's sequential, meaning that you have a pointer to go the particular location on those data structures, and you can also use like nonlinear data structures where you have to basically traverse back or outwards to backward or forward to find out the specific data in the memory. So you will see the differences in a better way soon. So in linear data structures, we have arrays, some linked lists, where you particularly say which links are, what the links are between the data types, data in the structure. You have stacks and queues. These are like, you have the data in an order, so one after another ordering. And in the nonlinear one, on the other hand, there are some complex relationships between the data stored in these data structures. So you can have hierarchical data structure like tree structures. So you have a main tree, and then it has two children nodes, and then they are connected. If it's a binary tree, if it's a quad tree, oak tree, you will see later you have 4 children or 8 children. But there are some relationships. Which one is the main node? Which one is the children nodes, and etc. You might have hash tables, some sort of graphs. If you study a little bit of machine learning, graph neural networks, or some foundational computer science courses, you have idea. You know already what graphs are. So there are these complex relationships, edges and vertices, etc., and heaps. Okay. So you can think of this linear as basically a line of students, or line of people, or the nonlinear data structures are like the family trees, which are usually complicated to read. Okay. So I would like you to remember as the linear data structures as data ordered sequentially. Okay, this is logically, not physically in the memory, and then you can have nonlinear data structure which doesn't have any order, sequential order. So how are you going to choose the correct data structure? It is purely application dependent, and you can use either or, the combination of these. So you use linear data structures usually when the elements are going to be accessed sequentially, or the data size is known a priori. Okay. So why do you do so? You can still use, of course, nonlinear data structures even in those cases, but since you already have an idea about the data that you will be using for that code, since the elements are stored contiguously, so you can ease your access to the data. You can make it more efficient. So random access is efficient in these cases in linear data structures. So you speed up your code basically by switching from nonlinear data structure to a linear data structure if you already know the data that you have. And then you can use the pointer arithmetic to access any element in the array. On the other hand, you might use nonlinear data structures when you have elements with some complex relationships, as we discussed, as I just said about the graphs, right? So you can use them basically if you have some hierarchical structure, or I mean, still you can build graphs so that you can easily access or make the search more efficient, although they are not sequentially ordered, but you can make them more efficient, and you can actually use them when you're going to insert something into the graph, or not only graph but the data structure. If you want to insert a new data, or if you're going to delete the data from the data set you have, you better use nonlinear data structures. So we'll see that difference in a moment again, but what I mean is, imagine now you have some sequential relationship in your linear data structure, and you're going to insert a new element in the middle of the array. What you're going to do is, so for the rest of the array, you're going to visit all these nodes and all these elements, and then move all of them to be able to put the particular one. But in the nonlinear data structure, what you care is basically just the relationship in the close neighborhood, in the near neighborhood of that particular element. And then you can insert a new element there and then restructure the neighborhood. So it is more efficient if you will be changing the data frequently. Then you better use a nonlinear data structure. So as you see, it's just an application dependent, and you have to keep that in mind and then program based on that. So we'll discuss a little bit of abstraction. So procedural programming is basically what we do with C, C++. So we build a program around procedures, around functions. Okay, so these abstract data types, abstraction is basically an object-oriented concept. So what it does is, you identify the key data types that you will be using, and then you encapsulate them in separate files. So you hide them from the user. Okay, you hide the details of how that data type works from the user. That is what encapsulation is. You put them in a box. Okay, and then you just expose the interface, just the functions or variables, to the users. Okay. The rest of the implementation is hidden from the users. That's the abstraction. And abstraction is important, so we can use the functions or the documentation without really knowing the details about how that function works, right? You use some built-in functions in C++, like print. Do you know the details of how print works? You don't know, but you have that particular name for the function, and then you use that function by knowing the fact that this is only for printing the whatever I give as an input, but you don't really care about the details. So that's the abstraction. And you build your own data types, you build your own operations through some abstraction, and it is an important piece of procedural programming. Okay, so now we'll discuss the abstract data types. So this is basically about what operations you will be performing without really saying how these operations are implemented, as I told you. So you, as an interface, you have just a name or some sort of variable that is exposed to the user, but you don't really, tell them how you do that operation. So you have the collection of data and some set of operations defined based on that data. That's the abstract data types. So we're going to have an interface for the abstract data, and then the data type. So we're going to have that interface, and the implementation is going to be hidden in that interface. Now I'll give you an example from real life in a moment. So this abstract data type basically it encompasses the data and also functionality on data. So you can think of this as a water dispenser. Okay. So in this water dispenser, the input is water, and we have this box, the wall, okay? So the data is water. And with that water entering this water dispenser, you can perform some operations, like you can get chilled water, you can get crushed ice, or you can get some ice cubes, or the machine can tell you that we are basically running out of ice, okay? So these are the operations that are exposed to the user. So what is the data structure? It's just internal structure of the dispenser. You don't really know what's going on there. So you define a new data type, the abstract data type, which is the water dispenser. Okay? But inside you have water, you freeze it, make it ice, and then you crush it, you get crushed ice or cubes, ice cubes, or you just cool it down and then you get chilled water. But those operations are hidden in the water dispenser. So the walls, the interface is just made of steel, which is the encapsulation. You basically hide everything inside that. So you get water as an input, and you give user chilled water, crushed ice, or ice cubes as outputs. Okay. So this is basically the idea of abstract data types. And it has an important use in procedural programming, especially when you write long, thousands of lines of codes that have to be used by various users with some expertise or without even an expertise. So you have to build your codes, your programs around these abstract data types or some sort of procedures. Okay. So let's look at a more realistic example instead of the water dispenser. So in C++, we have string as an abstract data type. Okay, there's gonna be, now we're gonna write that code. You're gonna see the code. I would like you to try after that these small pieces. Basically, I would like you to check how those codes work after the lecture. When the lecture notes are on. Ultra and available to you, you can go ahead and then write those codes and then check. Okay, so what we will do is we're going to create two strings, and then the program that you're supposed to write is going to compare the lengths of these strings and then print them if it is the same. Okay, the length is the same. So that is the abstract data type that we are building, basically. Okay, we're gonna input two strings, not even an input, it's gonna create two strings, compare their lengths, and it just gives you the output if the lengths are the same. Okay, so you can, when you're writing the code, of course, you have to understand the code in detail to be able to write the code. But if I'm going to be the user of this code, I don't really care about how you implement it, right? What I would like to see is, do I have this function, this program, and does it give me the output, these strings, if they are the same? Okay, if their length is the same. So that program basically looks like creating two strings, okay, hello and world, and it checks if the lengths are the same. Then it basically concatenates string 1 and string 2 and print them out. Print the concatenated string out if their length is the same. Otherwise, there's not going to be any output. So you can really program at a higher level without really worrying about the low-level implementation. Here also you can see you use the length function for string, and you don't really know how that is implemented, right? So this is just, again, another, I'll use the hierarchical word again in another context, but this is how you build the codes, build big codes in large codes in C, C++. Okay. So these abstract data types have a lot of benefits. First of all, as the name suggests, it provides abstraction from the implementation details so that you don't really worry about what's going on. Instead of, you just focus on what it does instead of how it does. Okay, so it's an important piece, so that you have some modularity in the code. Someone can work on that particular piece of the code, and then you can just use it for your own purposes. It provides some encapsulation, so user cannot access the internals. So you basically provide the code as well. So you don't, as long as it performs the work, you don't really let the user to change, to tweak the internals of the code. It provides some independence, so it reduces the number of interactions between the codes. So again, this has to do with the modularity. So you have these particular pieces, like the length of strings and the print function, but you reduce the interactions. Okay, you can change one piece of the code without needing to change the rest of the code. So that's an important bit again about modularity of the code. And when you work, in groups of people on large codes, this is what you need, the modularity. So flexibility, it's again connected to previous one, basically. Implementation change is transparent, which means that since you don't really care about the details of the code, you just know what you're going to give to that particular code, and then what you will get from that code. You can just change the rest of the code without changing that particular sub-piece, the subcode or the sub-program. So you can easily swap out one implementation with another. So you can change like a linked list with an array, for example, because these are only for storing the data. So you can either use a linked list or an array, but the code that uses them shouldn't really bother, as long as there's this data coming from linked list or array. And another protection is important. This is another important point. So it's a protection from our brain's limited powers to manage complexity in systems. So when you make your code modular, or when you build your code with small modules, you basically deal with you divide the complexity into smaller pieces, and then you deal with that complexity with less complexity, and then you bring them all together. It's like playing with Legos, right? So you build small pieces first, and then bring them together and build a huge one. Or you can give many examples about this from the let's say the production line. For example, you build for one car, you build different pieces: the engine, the tires you have, and the skeleton, and etc. But then you bring all of them together to build this complex device at the end. Okay, so these ADTs, abstract data types, they provide mainly modularity, and that modularity is essential for building large codes. Okay, and also there are the other advantages that I list here. So let's look at the ADT implementation. In C, you usually implement these new data types, abstract data types, with a struct definition. Okay, so you use struct to define the complex data, and then you expose a pointer to the struct. Okay, not the struct itself, so you hide the details. This is what I meant, basically. So the struct itself is a private to the ADT source file, but the pointer is exposed to the outer environment. Okay. In other languages, more modern languages than C, like C++, there are clearer ways to handle this. So basically, you define classes to group the data and functions together, and that is more convenient for large codes. So you have these classes separately, and then they have their own data variables. They have their own functions, which could be just private functions or some public functions as well. But it's more organized when you deal with the ADT implementation in C++ compared to C. Okay. So let's look at another example here. we're going to define a struct that in C that contains points in two-dimensional space. Okay, that's the implementation. So we define this new data type, which is point. It has two coordinates, x and y. So every point has two coordinates, x and y. And now you can see here down how I define it. I define a new point P1 with x 1.1 and 2.2. And I define another point P2 with x 2.2 and y 3.3. Okay? So the first question is, how does the memory layout look like? So first I create point 1, P1. How would be the memory layout? So I'd like you to think about it for a few seconds. Is it going to be sequential, physically sequential in the memory as in the layout, or distributed? Okay, so just think about it a little bit. Are they stored consecutively, x and y coordinates of P1, or you have x coordinate of P1 and then x coordinate of P2, which is basically a trivial question. If you go and look at the memory layout, you will see that for P1 you have the x stored in the memory with 8 bytes, so you get the y just stored consecutively just next to the x, so it is the same except the last digit changing from 0 to 8. So you store them consecutively basically. Okay, and then you get point 2, and then you can see here we have x ending with 0 here, and y it's the same except the last digit again ending with 8. So you store them consecutively. Now let's add some functionality in this data structure. Okay, we would like to implement a simple 2 norm for these points. So what we'll compute is, we're going to compute the square root of x squared plus y squared given a point. So we have this struct, again, the new data type, abstract data type, point, with two inputs, x and y, or two elements, x and y. So we create that point in the main function here with points 1.1 and 2.2. And then you build this functionality, new functionality norm, which basically calculates this. It takes the point P and then calculates the square root of x squared plus y squared. And then it prints that out. Okay? So let's look at the memory layout of this one. So I can ask you to play with this C function. You can write in C++ as well, but I just want you to see the memory layout for x, y, and the norm P. How do they look like? So for norm we have, when you implement it, you will see we have this one, and in the main code we basically create the point with 1.1 and 2.2 being the x and y elements respectively for point P. So they are in memory, they are linear. You can they are sequential. You can see consecutive. Sorry, I should use the right words because it can cause confusions later. You will see what I mean. And then when you create when you look at the norm, calculate the norm, you get, it's basically replaced by the so it basically replaces the first element over there, and it just returns the norm of these 2 points. Okay, so let's look at the example again. So now let's implement some initialization piece or some sub-program. Okay, so what you do is, usually when you have x and y as an input, okay, you create this initialization. So you say that p of the x element of p is the input x, and the y element of p is the input y. So this is how you input, how you initialize. In the previous slides, we were immediately giving the numbers, but now we send as an input. Okay. Here you can see at the bottom how you initialize it. Basically, you give the pointer to the p, array p, the first element of p, and then you say that the x and y coordinates of the p, these are going to be 1.1 and 2.2. Okay. So if you have a larger code in C, you have to name it different inits. Like basically, you have point underscore init. But in C++, as I mentioned in two slides ago, it's a lot easier because you encapsulate them into separate subfunctions within the structure. So you don't really worry about the naming. What you have is basically, in that case, you have different ints, different programs like point, and then the point has its own init. And then all the other relevant subroutines, some private or methods, private or public methods, just underneath that point. Okay. So if the implementation of the data structure changes, you can still keep the interface when you have an interface, something like that. So you can still get as an input x and y, but you can make it double, or you can make it integer, or etc. So you can change some underlying implementation, but you can maintain the interface as it is. Okay, this is all I would like to say about the abstract data types, how you abstract, how you do abstraction for specific data structures or for your new data structures. Okay, so now we're going to look at two main data structures, linear and nonlinear. So let's start with the linear data structure. Just recall, the structures are basically user-defined conglomerate types. What do I mean by conglomerate? So structures are basically bringing, they just combine different data types. You can have, inside the structure, you can have an integer, the student ID, you can have the student name as a character, and you can have the student's GPA, okay, the floating point. So this is a structure. It's called conglomerate type because, as you see, you can combine different data types, and then you can create this student structure. Okay, so structures are pretty useful, but again, it depends on the application. So it can introduce some performance and ergonomic issues by themselves. What do I mean by that? I mean, instead of using arrays, you can, of course, still use structures. You can have structures built by integers, but in the structure, what you do is you basically you do additional padding, so you allocate more than what you need. Okay, because you don't specifically say what you will need. You just have that structure. It can be considered, it can be built by an integer. It can have an integer, it can have a character or float. So it just generates more than what it needs, just to be on the safe side. So if you deal with large data, that's not an advantageous thing. And then, so structures, you might have some arrays of structures. So basically you can include the student ID, name, and the GPA. But imagine you don't need all the fields about the student. You just want to fetch the student ID from that student structure. So you might have some cache misses in those cases, because all the one student relevant things like the ID, name, and GPA, they're going to be all stored together contiguously, and then you'll have the second student. But ideally, you just need, in some cases, just student ID. Okay? In those cases, you unnecessarily store name and GPA in the cache, and then you have some cache misses. And why is it important? You've already seen, possibly, that it's a lot faster to reach out something in L1 cache compared to reaching out something in RAM, right? If you do this millions of times, billions of times, of course it's not efficient. So you have some performance and ergonomic issues. What do I mean by ergonomic issues? So then the syntax in C for structures, as you can see here, it's a bit verbose. So ergonomically, it's not efficient either. And you might have some naming conflicts. What do you do in those cases? So if you're going to deal with some sequence of numbers, and then you're going to do some simple operations with those sequence of numbers, you better use these particular data structures, arrays. These are continuous regions of memory, okay, holding sequence of values. So basically these are, they have linear relation. They're all, one repeats one comes after the other one, and then on the memory layout you have them as in a contiguous way. Okay, so computers are good at really doing simple operations to a sequence of numbers, and hence you use arrays to very frequently for scientific computing. That's why it's called that. We have that sentence. This specialty makes arrays the bread and butter of computing. Okay. One thing that you have to keep in mind that values in array have a fixed uniform type. So you say that this is an integer array, so you always have integers, unlike the structures as a conglomerate data type. Okay, and then you access the values in the arrays using these brackets. Okay, you go to the third element, and then you change it to 3, or you can also use pointers to directly access the memory of that array. So basically, when you have this ARR, it refers or it points to the first element of ARR. Okay, if you say +4, so go to the fourth element of ARR, and then you have this pointer over there. Okay, so ARR by itself is a pointer to the first element, and then you can directly access the memory by the offsets here, as you can see. So it comes with a lot of easiness for the application. So we'll discuss now the arrays of structures and structures of arrays. So let's look at an array of structure first. So we have a structure, person. It's a conglomerate data type. It is an integer. Age is an integer, and the weight of that person is a double data type. Okay, so that's the structure. And then now we create a couple. Okay, that's an array of structures. So we'll have two people, two persons, two people, and we're gonna create this array of the persons or array of structures. Okay. So how are these entries stored in the memory? You will have basically the first element of the couple, 0th element of the couple with age and the weight, and then you get the second entry, second element with its age and the weight. So you have the first person with its age and weight, as we've already seen in the memory layout for points. So you have the first person age and weight, and then the second person age and weight. Okay? So basically the increment 0 to 1, it points to the subsequent age. Okay? Let's keep this in mind. Now imagine we want to access all the data belonging to the first person and all the data belong to the second person. I would like you to consider think about if this is an efficient way of storing the data or inefficient way of storing the data. So we would like to access all of the elements, all the data for the first person, and then all the data for the second person. You have to answer this question by thinking out about the memory layout. Okay, so I'm giving you a few seconds to think about how to do if it's efficient way of storing the data or not. So it's an efficient one because this is how the things are stored in the memory. You have possibly less cache misses. you'll have one person, all the information about that particular person, and then you have the second person, and so on and so forth. But what if we want to compute the average of age only, or the average of weight over a group of people? So we'll only reach out the age of all the persons in this list, okay? Not the weight. So it's really unnecessary to keep the weight in the cache if you would like to compute the average of age. Okay. So this is not an efficient way of storing data. In that case, you have structure of arrays, basically the arrays of ages, arrays of weights of these people, and then you have their structures. Okay. So this is an important concept in programming with C, C++. You have to consider how you will access this data. Okay, how you will need the data, how you will group the data. So that's why there's always this competition between arrays of structures and structures of arrays. Okay? So you can have structures of arrays, like I have the array of age, an array of weight, and then I have the age structure keeping all the age, or I have one big structure keeping all the arrays. The first element is just the ages, the array of ages, and the second element is the array of weights. And I want to make operations on the array, the ages or the weights only. So you can make vectorization easier if you use structure of arrays in those cases, because you can call all the ages and then vectorize the operations on the ages easily. Okay. So if you like to loop over only one field, one data field at a time, structure of arrays is a lot better compared to arrays of structures. If you like to access all or many of those fields together, then you better use arrays of structures, because in those cases you'll have, as it is written here, you have the data locality for these accesses. So you have all the ages and you have all the relevant information from one element, one field. So let me put it this way. So you have an access to all the fields of a particular element of the particular structure in the array. Then you have that data just around, in that neighborhood. So you access to the weight of the age of the person, and then the weight of the person is just in the neighborhood. This is data locality, what I mean by data locality. Okay. You can also use a hybrid approach. It could be occasionally useful. So what I mean is, now imagine you have point masses in the space, okay, and these masses move with some velocity. So you have information about, so you have a bunch of points, you have velocity, position, and mass associated with these points. So which ones are used together? You can use velocity and position together if you want to calculate, let's say, some forces, repulsion forces. You want to calculate the momentum, and not momentum, sorry, that would require the mass as well. You want to, let's say, calculate the relative velocity, relative position, some force because of their relative positions. So you can put them together, because whenever you want to reach a point, you like to reach both the velocity and the position of the point. But then the mass is irrelevant if you're not going to calculate the momentum. Okay, if you would like to calculate the gravitational force, what you need is only the mass in those cases. So you can access mass independently, and some position as well. You can then combine mass and position, or you can combine velocity and position, or you can combine velocity and mass if you want to calculate the momentum. So you can build a structure with two elements, mass and velocity, and then you have, so that's for one point, and then you have arrays of these structures, so the points, so that at any time you can reach both information of the same point. Okay, so you can have this hybrid approach. Another example here is the molecular dynamics. Basically, you were going to calculate so we have two molecules as an input to calculate the distance between these molecules. So what you do is you go to the x and y elements of these molecules to calculate the points of these molecules to calculate the distance, relative distance. It's a computationally demanding application because if you have n number of molecules, you're going to perform order n squared operations to calculate the positions to distance between these molecules. Okay, so naive implementation is a quadratic complexity, which is not acceptable. You have to reduce it to order n log n. Okay, so think about the issues that can arise in this code regarding the memory subsystem. Okay, how things are laid out in the memory. Okay, think about that. And what is the computation complexity? I just told you it's order n squared. Okay, how can you speed this code up? So what you do here is, for example, you loop. Let's say we have 20,000 molecules. Okay, and then you build some sort of, you're gonna look at the distance between all the molecules just to calculate the force. So you have this kind of for loop, but then you reach the molecule I, the ith molecule, and you go get the x coordinate and the y coordinate of that one, and then you're going to reach out some really far away from that molecule laid out in the memory as well, and you're going to get the x and y coordinates of it. So you don't really look at the points that are closely linked to each other in the arrays. Okay, so you can build, this is a hybrid, you see some hybrid implementation. So you have the molecule as an array of structures. Okay, so every molecule has its two coordinates and the mass related to it. So you create 20,000 molecules with two fields for each, or you can have the arrays of the x points, x coordinates, arrays of the y coordinates, and you can also have an array for the mass of these molecules. So you can implement it in both ways. Okay, you can play with it and then see which one is more efficient. That's just an exercise that I'd like you to do. So for this molecular dynamics example, please go implement structure of arrays and arrays of structures to keep the positions of the molecules and also to keep the masses of the molecules. But mass is really not relevant here, but the points x and y coordinates of the molecules, and then calculate the distances just to see which one is more efficient, okay, in terms of memory layout. So overall, the problem with this arrays is that, I can give you some hint before moving on here. You have significant performance differences, and with the structure of arrays you will see that so with this one you have better cache efficiency and parallelization. So you have first the x coordinates, so the x coordinates are just consecutive, and then you'll have the y coordinates which are also consecutive, and that's a lot better than keeping molecule A x and y and then molecule B somewhere else x and y. Okay, you'll see that difference. So it has better cache efficiency, and it's going to be a lot easier to parallelize the code. You can imagine how to do it. Okay, it's a good thought experiment, and you can also play with it with just simple tool how to optimize these two nested for loops. Okay. So arrays, I told you that there are many advantages about the arrays because these are special structures based on numbers, and then in scientific computing we perform a lot of simple operations on arrays. So we usually parallelize these operations, and arrays allow us to parallelize efficiently. But if you're going to insert or delete an element at the beginning or in the middle of the array, this is inefficient. Now, imagine you want to insert an element at the start of the array. What are you going to do? How many elements do you have to visit if you want to implement one array? One element. If you want to insert an element at the start of the array. Now, at the start of the array, you're going to insert a new element. So its memory. You're going to give it a memory address, and then you have to visit all the elements to update their memory addresses. Okay. So you're going to reallocate to increase the size of the array because initially the size is the same, and then you're going to move all the elements out of the way. Okay, and then you can now write to the first entry. So it's an inefficient application if you have inserts and deletions. Okay. But now imagine if you don't really care about storing these elements in a sequence, so you can allow the storing of these elements out of the sequence, then you can place the new element anywhere in the memory. Okay? Then how do you get the next element in the memory in those cases? You have to put a link. Basically, you have to tell this element is linked to which element, the next one. So you put another pointer to basically tell what is the next piece of data. So this is still linear, although it's not sequential in the memory. So physically, these are not consecutively laid out in the memory, but there's a link from one element to the other element. Okay? And that link is the pointer. This is different than the nonlinear data structure. In the nonlinear data structure, there's a relationship. Okay, no link. There's a relationship between the elements. But in the lists or these linear data structures, you know what the next element is. Okay, you know the pointer to the next element. So now let's discuss the linked lists. In the linked lists, we have data and also the pointer to the next piece of data. Okay, so the elements are no longer stored linearly stored is not the right word here, but they're not stored contiguously in the memory, consecutively in the memory. That's a problem because now you cannot move to the next element just by incrementing the address. You need a pointer to the next element. But otherwise you knew that, if this is my 0th element, the first element is just incrementing the address. Okay? So now we have to explicitly keep track of where the next element is using a pointer. This is a bit easier when you're going to insert things inside the list. So let me show you how that works. Basically, we have this let's say we have the first element 1.1. You store this float string number, and then you have the pointer, which basically tells you what the next element is. So this is still a linear list because one comes after the another one, but you don't explicitly know, or you don't inherently know where the next element is. So you have to put this pointer, okay? And eventually you have a last pointer, which is usually a null pointer, which tells you that this is the end of the list. Okay. You might have a double linked list in a single linked list. Imagine now if you delete one element, since it tells you what the next element is, you're going to break the chain, and now you have to create new pointer or the new links to still keep everything linked in the list. So you can have a double linked list. Basically, you can tell what the pointer, you can also specify the pointer to the previous element and the pointer to the next element. That could be more robust, but then you might need to traverse the entire list again, so it's not really efficient. And also you increase the, this is also storage. You don't only record. So if you were storing as an array, you would just have the middle element in your array. In the single linked list, you have array plus the pointer. In the double linked list, you have array plus 2 pointers. So you increase the size of the storage, but they come with some advantages. And these are, you might also always say that, well, these are really small advantages that you're talking about. That is true if you deal with small number of points, but if you're dealing with large data sets, they make huge differences. So you can try and experiment with those. Okay. So with the linked lists, you basically do a treasure hunt. So you start with the first point, and then you follow the clues to get some sequential access. So you iterate through the list in one direction. There's no random access. What I mean here is basically you don't access the elements in constant time or O1 time, yeah, because you don't know. You cannot just increment the pointer address and get the next element. So you need to traverse. You need to go through the nodes to find out to follow the links to find out which element is where. So that doesn't give you random access. Random access is, in that case, you know the pointer, and then you can, for any point, you can easily reach to that point with constant time. But you have a linked list, then you have to follow the pointers. Just go to that element in the list, look at the pointer where it points, go to the next node, next element, and see if it is what you're looking for. If it's not, then you go to the next one. So you traverse the elements, and going from one to the other one, it is a bit time consuming. It's not efficient. In a single linked list, losing a pointer loses the rest of the list. That's a big issue. So you can use a double linked list. But then there are also, you might ask, why shouldn't I use double linked lists all the time instead of single linked lists? Well, it uses more memory per node. And then, as I told you, it's not a big issue if you have few nodes, but if you have billions of nodes, hundreds of billions of nodes, you might have issues. When you insert or delete a node in the list, then in the double linked list, now you have to update both links, not just one link, so the previous one and the next one. So ergonomically, again, you might have some issues. It's more error prone. You see what I mean? So single linked list is simpler, faster, since it's just one forward traversal, so you always go in one direction. But double linked list is there are some safety involved in it, but then it's also more error prone still and slower. So you might use double linked lists when you have too frequent deletions and backward traversal, like undo, redo operations. Okay. So as I told you again, linked lists could be advanced. In scientific computing, we don't really use arrays or some trees where we know the hierarchical relationship, and there's a hierarchical relationship. But if you have some deletions and insertions frequently, you might use still the linked lists. But you have to iterate through the lists, and it is inefficient. Okay, and as I told you, there's this memory overhead for storage of the pointers. But yeah, overall, I can tell you that you can still use them. For example, for a grid where you like to control the order in which cells are traversed and computational load on each cell is high. Okay, so there are some uses of the lists. The size, you don't have to predefine the size. It's dynamic size. But the disadvantages, in summary, is that there's no random access, there's extra memory overhead for pointers, and it's not really good for the cache. Another linear data structure which we don't really use is stacks and queues. So stack is like a data structure where you basically push, okay, the last in, first out. Okay, it's called LIFO, last in, first out. So you push the data or pop the data. So you put new data in, and so this will be the last element, or you pop the data, that will be the first element that you push, that would go out. Okay, you can use them. We don't use them in scientific applications, but you can use them for undo operations or some recursive calls. Queue is the other way around, so first in, first out. So you implement, you can still use both at the same time. So you will put just the point in, okay, and then you can queue it at the back, and then you remove from the front, okay. So it's like a print queues or customer service lines. So that's the queues. The data structure is a data structure. You can implement both using arrays or linked lists with pop and push operations, but these are expensive because now you have to use the every element. So as I told you, I'm just giving you them as some information that you might need later on, but we don't really use them in scientific computing. Okay. Now we're going to move to the nonlinear data structures. Again, just to make in your mind clear, with linear data structures, so linked lists are still linear, okay? Because logically these are linear. I'm not talking about the memory layout. There's always a link between one element to the other element. So that's what I mean by linear data structure. There is a link between one element to the other element. It is either increasing the pointer and reaching to the next element as in arrays, or I store the pointer to tell me what next array is. So you can make the linked list more efficient if there is a relationship, some hierarchical relationship. Okay? And that is the binary trees. So this is a definition from Wikipedia. Let me read it. So a node in binary tree, this is a tree with $2 cells. Okay? A node is a structure which may contain data and connections to other nodes. So these connections are sometimes called edges or links. Each node in a tree has 0 or more child nodes, which are below it in the tree. Okay? So trees are drawn with descendants going downwards. It's like a family tree. It starts with the highest, the eldest member of the family. A node that has a child is called a child's parent node or a superior, and all nodes have exactly one parent, except the topmost root node, which has none. So you can see the structure. There's some sort of structure. If you, let's say you reach out one of the daughter cells, the child cells, child nodes, and you know the connection to the superior node or the parent node, and then you can find out if you have another node, which is the sibling of that node. They share the same parent node, so you can find out the parent easily. You can say that these are two children of the same parent. Okay, there's some sort of connection between them, so it's a lot easier traversing. There are some advantages when you traverse the tree up and down. So binary tree is actually a special case. Every parent has exactly 2 children, and you can see the implementation. So one node, it has the data kept, and it also keeps basically 2 pointers to the left and to the right child. Okay, that's a binary tree. In scientific computing, we have quad trees and oct trees. These are, you can imagine like a grid. So quad tree is a grid in 2D. You basically divide your grid into four nodes every time. So that's a quad tree. An octree, it has the tree with 8 child nodes. So you divide your element into 8, the cube, 2 to the cube. Okay. And each node basically consists of a data, or it's usually a structure, and pointers to the 2 children, as you see below here. Okay. So when you traverse the tree or when you search, the complexity is order log n when you have trees. So they are more efficient compared to the linked lists when you go around. But as I told you, it's not logically linear. There is some sort of relation between the nodes based on, it is geometrically related or some sort of relation which tells which nodes are sisters, which nodes are parents, and etc. And what do I like to tell? So it's efficient in searching. As I told you, it's natural hierarchy. It's built in. The natural hierarchy is built in the code as well, the program that you have. But then you have to balance the tree that we're not going to discuss, but you can search what's a balanced binary tree or quad tree, octree. Why is it important to have the balanced one? So in order to get log n complexity, you need a balanced tree. Basically, every node has 2 children and so on. But if the nodes don't have 2 children, most of them don't have 2 children, but one has, or few of them have 2 children, then it's an unbalanced node, and you're going to waste most of your time looking at the other ones. Okay? Now that's why you need to balance the tree. And of course, since you have again 2 more pointers, it takes more memory than array. But it has some advantages, as I told you. So they are pretty commonly used in hierarchical algorithms, such as multigrid algorithms or Barnes-Hut or fast multiple method, which are commonly used in physics applications. You can look at some particle simulations. You can look at the galaxy simulations where you use these trees and to make your code faster. Okay, and that, as I told you, that helps you to sort or search the points, the elements efficiently, since the search is, or traversing the tree is, or only log n complexity compared to n squared complexities that we discussed before. But there are some pros and cons that you might wanna think about them. So the pros, as I told you, it's efficient in searching, but the cons are that you better have some sort of balanced tree structure. So it takes some effort to implement it efficiently. However, if it is implemented efficiently, you can take the most out of that. So overall, we discussed the data structures today. So choosing a data structure is like balancing speed, memory, and operations. So they're all application dependent. There are many available data structures, but they're all application dependent. And choosing the correct data structure has a huge influence on the code performance, because you first, how you reach out the data. Are you reaching out the data from cache or from RAM? So the data locality is something that you have to consider, so that you can access the data quickly or slowly. And also the memory layout. So are you going to use more pointers that you actually need, or you can actually store everything in arrays? That's something that you have to consider. So considering the structure of the data, do you need to identify the related data? Right? That's something you have to again think about. So you have to, link them, or it's just the incrementation is fine, or there's some complex relationship that you have to put in. And then are you going to insert, right? The operations, think about them. Are you going to insert new points or delete? So then maybe you better use linked lists, or your insertion and deletion is in specific order, so you can maybe use stacks and queues. Okay, again, application dependent. And in scientific applications, you can also think about how I'm going to reach the data, the portion of the data, which ones are called together. The example that we discussed, like distance and position, are we going to reach them together or separately? So then you can decide on array of structure or structure of arrays. Okay, which one are you going to use in common? And if you have a hierarchical algorithm, you better use a tree-based structure. Okay, these are pretty common for scientific applications again. And then think about how your data structures are going to use. Okay, you're going to build this interface like the water dispenser example. So you'll have this API that can make your data structure usable without really understanding the entire implementation. So are you going to work with a huge group in which everybody is responsible for different portions or different pieces of the code? So maybe in those cases you better have some abstract data abstraction and hiding the implementation underneath, so that you make your code more accessible, easy to read, and more robust. So these are the things that you have to consider when you decide on the data structures in the code, and it's a pretty important topic. That is why I've discussed the relevant ones today. So I'll give you one example, one Jupyter notebook where you can play with these concepts. So I would like you to keep this always in your mind. Data structures are the foundation of algorithms. Okay, and real-world software, it is becoming more and more important as the data size increases exponentially. So it is important how to store the data, how to access the data for efficient use of the resources that you have and for fast codes. And you have to master them to be able to write efficient and reliable programs. Okay, good programmer is a master of the data structures, accurately uses the data structure to, efficiently use the data structures to design the code. And you'll have the slides, so I also encourage you to implement these structures or these sub-programs that we discussed, little programs that we discussed today. They are mostly written in C, so I suggest you to write them in C++ as well. So these are really nice experiments or the toys for you to play with. So with that, I would like to thank you for attending today's lecture.